Hi folks, welcome to AP Calculus. Today we're going to focus on the derivatives of the inverse trig functions. So you'll remember that the inverse trig functions can be written in two different ways. Y equals arc sine of u means exactly the same as y equals sine inverse of u. So no matter which way the function is given to you, we're going to do the derivative in exactly the same way. So you may have to pause the video to write down these formulas. There are 6 of them for all 6 inverse trig functions. Let's take a notice though. Let's look at the derivative formulas. If I've got the inverse of sine, so arc sine of u, the derivative is going to be u prime over the square root of 1 minus u squared. You'll notice that our cosine is exactly the same rule, except that it's the negative answer. For our tangent, we're going to say u prime over 1 plus u squared, and as you can guess, the inverse of the cotangent is going to be the same as the inverse of the tangent, just the negative. So copy down these 3 rules, and then I'll post the next 3. So take a few minutes to pause the video and write down all 6 rules. Now the one that's a little bit more complicated are the arc secant and the arc cosecant. Again, these 3 functions can also be written in the inverse notation. So arc cotangent could be written as cotan inverse of u. And again, as stated before, the arc cotangent rule is just the negative of the arc tangent rule. Arc secant and arc cosecant are a little bit different. Our numerator still starts with that u prime, but for arc secant and cosecant, you'll see that you have an absolute value of u in front of the radical. Notice also that the radical is exactly the opposite of the sine and cosine. This time I start with the u squared and subtract 1. So write down these rules as well, and then we'll do some practice problems. The derivation of several of these rules is in your textbook, so if you are interested in where these rules come from, you can follow the derivation in your textbook in that section in Chapter 5. So let's go ahead and take the derivative of several of these inverse trig functions so that we can get a hang of the way that the formula is going to be used for the derivatives. Again, as has been the case for this whole chapter, it's going to be important that you know these 6 rules. Because there's really only 3 and the cos are just the negative of their function, there's really only 3 to memorize, and then just know which ones are the negatives of the others. So if I've got y equals arc sine of 4x, the rule for arc sine for the derivative is y prime is equal to u prime, so my u in this case is 4x, so the derivative of 4x is 4, over the square root of 1 minus, now I've got to square the whole 4x, so when I square that whole 4x, that's giving me a 16x squared. And that's what's involved with taking the derivative of the arc sine. Now, of course, sometimes we'll be asked to take the derivative at a certain x value, so then we'll just substitute that x value in. This will all be predicated, though, on using the correct domain for arc sine of 4x, because if I'm plugging in a number that doesn't fit into the domain, I'm also not going to be able to take the derivative. For number 2, I've got the arc cosine of radical x. So you'll recall that the derivative of arc cosine is the same as the derivative of arc sine, but we're going to negate it. So off to the side, you might want to say u in this case is equal to the square root of x, which we all know that x to the 1/2 is exactly the same thing. So when I do my u prime, I'm going to have to say, using the power rule, 1/2 x to the minus 1/2. So I'm going to go ahead and substitute that in, and then I'll deal with taking care of the negative exponent. So for my y prime here, we're going to say the negative of u prime. So right now I'm going to write it as 1 over 2, and I think I'm going to write that as a radical x in the denominator of the numerator all over the square root of 1 minus u squared. So when I square the square root of x, that's just giving me an x. Now, as is always the case, we're not going to leave our answer as a complex fraction. So I'm going to multiply the numerator and the denominator by 2 radical x. So when I do that, in the numerator that's going to cancel. So now I'm going to have a negative 1 over, in the denominator I can distribute that radical x through the other radical, so I can say that it's 2 square root of x minus x squared. And of course we all know that in both of these answers we cannot take the square root of any term under a radical that's being added or subtracted to another term. So in both of these cases, that's our final answer. For our third example, let's take a look at a different function. So this time we've got the inverse secant. So y is equal to the arc secant of e to the 2x. Now again, I'm going to come off to the side and say u this time is e to the 2x. So let's do the derivative. So the derivative is going to be 2e to the 2x. So let's go back and plug it into our derivative formula for arc secant. So I'm going to say the derivative goes in the numerator. Now let's see here. Secant is going to be the positive one because the cosecant is negative. All the cos are negative again. So this one's going to give me a 2e to the 2x over, now watch how this works with secant. I'm going to take the absolute value of the u. So the u is e to the 2x. And then underneath my radical, I'm going to say the u e to the 2x has to be squared, and then I subtract 1. Now, a couple things that I can note here. First of all, e to the 2x, because I know what my graph looks like for e to the x, e to the 2x is always positive. So since it's always positive, that tells me that I don't even have to put it inside absolute value. So my answer right now is y prime is equal to 2e to the 2x over e to the 2x, not necessary to have the absolute value, times the square root. When I'm squaring e to the 2x, I raise a power to a power by multiplying, so that's going to be e to the 4x minus 1. And because I have the same e to the 2x in the numerator and the denominator, that can cancel. So that's giving me y prime is equal to 2 over the square root of e to the 4x minus 1. So it's really nice that I could cancel off that e to the 2x, but the only reason that happened was because e to the 2x was a function that was always positive. Remember how I told you that e shows up in a lot of examples, especially on the AP exam, because of the nature of the function e to the x. It's really helpful in doing some math with e to the x. Now, we want to find this derivative when x is equal to 1. So we're going to say, oh, that's not too difficult. We're going to substitute 1 in for x. So y prime is equal to 2 over the square root of e to the 4 times 1 minus 1. Now, in an example like this, I'm just going to leave my answer just like that. If this were an application problem where I would need a value for this, what I've shown you right now is called the exact value. I didn't do any rounding. It's exactly what my answer is. But if I want an approximate answer, I could, of course, put this on my calculator and round it to 3 decimal places. Now let's go ahead and try 2 more examples where the inverse trig function is part of another function. So for example, in number 4, I see that I've got g of x is equal to arcsine of 3x over x. Now don't forget our basic rules here. We see that, oh, I started to write down product, but this isn't a product. We're going to have to use the quotient rule for this one because I do have a quotient here. So let's see how the arc sign is going to be included in this quotient rule. So g prime of x is going to be equal to the derivative of the numerator. So that's an inverse trig, so I'm going to say u prime over the square root of 1 minus the u squared, so that's 9x squared. So the derivative of the numerator times the denominator, so let's multiply by x there, minus the derivative of the denominator, 1, times the numerator, arc sine of 3x, all over the denominator squared. Now, of course, our last step is going to be to eliminate this complex fraction. So I'm going to multiply each term by the square root of 1 minus 9x squared because, of course, that's my least common denominator. Okay, so in the numerator, the 1 minus 9x squared underneath the radical will cancel. So that now gives me that my derivative is equal to 3x minus, I might write this as the square root of 1 minus 9x squared times the arc sine of 3x all over x squared times the square root of 1 minus 9x squared. And that's my answer in simplified form for the derivative of this quotient. Let's finish up with example number 5, where again I see that I have an arc sine. It's a really basic one, arc sine of just x. But then I see that I've got a product involved. So over here we're going to have to use the product rule. This looks like it's going to be an interesting combination. So when I take my derivative, the derivative of the arc sine is going to be my u prime, so that's 1 over the square root of 1 minus x squared. But then I'm going to have to use my product rule, so I'm going to say the derivative of the first, that's 1, times the second, square root of 1 minus x squared. But then when I try to take the derivative of 1 minus x squared, remember that that's the same thing as 1 minus x squared to the 1/2. So when I take that derivative, I'm going to bring down the 1/2, keep the 1 minus x squared, but this time it'll be raised to the negative 1/2, and then I'll multiply by the derivative of the inside, negative 2x. I'm going to go ahead and cancel off those 2's to make this a little bit easier to simplify. So recapping here, I've got the derivative of arc sine was right here. I started my product rule by saying the derivative of the first times the second. And then I want to add on the derivative of the second. So that's what I went off to the side to do. So that's going to be x over the square root of 1 minus x squared. And then that has to be multiplied by the first term, which is the other x. So that's going to be an x squared incorporated into that numerator. So let's see here. It looks like I do have some common denominators. So let's go ahead and add those two terms together. So I've got that y prime is equal to x squared plus 1 over the square root of 1 minus x squared. Wouldn't it be fun to multiply the numerator and denominator of that second fraction, or that second term, by the square root of 1 minus x squared? In that case, I would then have a common denominator for all of these terms. And look at the simplification in the numerator there. We're going to say square root of 1 minus x squared times square root of 1 minus x squared. That's 1 minus x squared over the square root of 1 minus x squared. And an example of this might be like on the AP exam, a multiple choice where I've got to match answers. Adding together my numerators, I'm getting a 2 over the square root of 1 minus x squared. So while this looked like a pretty complicated problem, the terms ended up adding together because they were very common, and I could come down to this pretty simplified answer. So what I'd like you to do is work on the practice problems out of your textbook for taking the derivatives of the inverse trig functions so that you'll be ready for our test next week. Thanks for watching. Have a great night.